Okay, welcome back to the session, right. So, in the previous session we will discuss in detail about controllable canonical form, right. In today's session we will discuss about the observable canonical form, right, and the other method also. So, in the observable canonical form we have to assume again the same transfer function, and why we are using this, because it is giving us the impact of state variable on the output. So, how our state variable present in the system changing the output, this study can be obtained from observable canonical form. So, whenever we design a controller, so our aim is to make it as a observable or observer. So, whenever we have to make a observer system, so we have to go for observable canonical form. Okay. So, again to how to obtain it, we will use this expression, that is ys over us, that last time that we used. Okay. Same expression would be here and the step would be different. So, here we need to write this expression in terms of y. In the previous case we were observing expression in terms of x of s. Okay. So, now we will see what is the basic difference coming here. So, here we need to write this expression in terms of y of s. So, again this step would be same, multiply by numerator and denominator by highest power of this s raised to power minus n and s raised to power minus n, okay, in numerator and denominator, right, and then the equation will become like this, and now we have to solve it. So, here I need to write this in terms of y of s, because I have to observe the output. So, this will be my expression, I will multiply y of s with the whole expression. So, I will get here y of s plus a n minus 1 s inverse plus dot 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 will go on. So, I will keep this y s in the LHS and remaining variable in RHS, and this expression will form. Okay. So, now we need to see the position of state variable that we have to keep in descending order from right to left. It means the node near output, it would be of power of x raised to power n, and node near input would be my x 1 state vector. Okay. It means my x 1 state vector would be here, not power of n, it would be x 1 state vector or nth state vector will come near output, and the first state vector will come near the input. So, this would be different in case of controllable canonical form. In the CCF we have to keep highest power near the input, okay, and lowest power of state variable would be near the output. So, this is happening in happened in CCF, and this change will come in OCF. Okay. So, I will show you this how it is happening. So, by writing this equation I write to need again draw the SFG for it. Okay. So, this SFG will form here, you can see that we are observing x 1 dot here or x 1 near the input and x n near the output y, and this would be the diagram. And if we compare with the previous case, this was my diagram. So, I assume that the counting of my state variable x 1 is here, this node is x 1 dot, this node is x 2 dot and x 3 dot. In the same way last node would be x n dot. So, I have to start in a ascending order in case of CCF, and this was the SFG. In case of OCF I have to start in reverse order, highest state vector will be or state variable x n would be here and lowest x 1 would be here, you can say x 1 will lie here. Okay. So, this is the difference in between CCF and OCF, and this different diagram will obtain. You can do yourself, and whatever process that we followed in the previous case, same process we can follow here. So, to draw this SFG we can follow the Mason's gain formula that we used in unit 1. So, this is again a alternate method to obtain this SFG, right. It means you are getting the transfer function like this ys over us equal to suppose 3 s square plus 2 s plus 1 divide by, you can say, 4 s cube, or assume at s cube plus 4 s square plus 2 s plus 2, right. So, what is our first step? We need to multiply numerator and denominator by s raised to power minus 3, okay, and then we need to solve it. This will become you can say 3 S inverse, this will become 2 S inverse square plus S inverse cube. In the denominator I will get 1 plus 4 S inverse plus 2 S inverse square plus 2 S inverse cube. This will obtain, right. So, in this case what we need to do, we have to assume numerator part as a feed forward path or forward gain. Okay. And this denominator expression can be written as 1 minus of minus 4 S inverse minus 2 S inverse square minus 2 S inverse cube. Okay. This will be the loop gain, right. So, 3 S inverse is here. So, from here you can say this is my input u, the top one would be 3 and S inverse integrator is present here. So, here I will get 3 S inverse. In the same way 2 S inverse square is here, it will start from here 2, coefficient would be 2, S inverse will be here, S inverse, this will make 2 S inverse square, it will goes to the output. In the same way 1 times of S inverse cube, this third line would basically be the S inverse cube, coefficient of 1, S inverse, S inverse, S inverse. If it is unit, it means in between this node and this node I am getting single S inverse, assume it to solve this problem. So, I will get this type of graph. Now, for denominator I am assuming the loop. So, 1 minus, you can say minus of 4 S inverse, right. This is the one loop, it means this is my S inverse gain, this is my feedback, here loop gain is minus 4. Okay. In the same way I have to obtain second loop S inverse square. How you can obtain this loop? You can start from this node S inverse square and come back via feedback with coefficient of minus 2. In the same way if I have to make S inverse cube, start from here, come back to the feedback and you have to make this coefficient of minus 2 S cube. So, in this way via Mess's gain formula you can draw the SFG. So, multiple options are available in which you can say which one is comfortable, you can follow that method. Okay. This is the OCF method. Now, we will come for the next method, cascade method. Okay. So, in the cascade method what we will do, our transfer function should be in a factored form or you can say in terms of poles and 0, right. So, in cascade method it is also known as the parallel method. Okay. So, here what we need to do, we have to obtain our transfer function in terms of factored form. You can say the above numerator will gives us the basic zeros and the denominator term will gives us the poles. Okay. So, we need to convert our transfer function, you can say if I am getting the generalized expression like this. So, I have to convert this transfer function in factored form and after factorization this will gives me 0 and this will gives me the poles. So, I have to convert in factored form to obtain the cascade method or parallel method, right. So, here I am taking a separate example, y s over x s is equal to s plus b over s plus a, then I will come back to this transfer function to make the SFG. Okay. So, here what I will do, I have to multiply numerator and denominator by highest power present in the denominator, it is s power 1. So, I will multiply it by s inverse in the numerator and s inverse in the denominator and I will obtain this expression. Okay. So, here I can convert it in terms of Mess's gain formula. Okay. So, here this will be my forward path and the denominator term I can write 1 minus of a s inverse, this will gives me the loop gain. Okay. So, here my input node is, suppose that I am assuming this is my input node and this is my output node y. Okay. Now, we have to do what, we have to arrange our input, you can say my I will follow here basically the CCF format. So, the lowest you can say state variable x 1 will come near output, and the highest will come near the output, sorry, near the input. Okay. So, the highest term is here x 1 only. So, x 1 dot will come near, sorry, this is the input, and this x 1 will come near y, that is the output. Okay. So, here is feed forward path, one is one element is here 1, we can say. So, this is my input, I have to go from input to the output with gain of 1. So, I am modeling this expression 1 plus the alternate method to reach the output is B s inverse. So, I will make here a gain of 1 by s, it will reach to this node. Okay. And what is the gain of this node is B, I will add B gain here and it will reach to the output. So, this is B s inverse and 1 is coming here. So, y equal to 1 plus B s inverse. So, in this way I can model my numerator part. For denominator part I have to look for the loop gain, S inverse is present here and here gain is minus of A. So, I have to complete this loop with minus of A, and this loop will gives me the denominator part 1 minus of A s inverse. So, in this way you can make a generalized concept, the numerator part will gives you feed forward path and the denominator part will gives you the basic loops or feedback loops, right. So, in this way we can make the SFG for such type of expression. So, now I can divide this expression into 3 part, one is k, second is s plus b 1 over s plus a 1, I am assuming as a second part 2, s plus b 2 over s plus a 2, I am assuming it as part number 3. When I combine it, then I will get the complete transfer function. So, I am doing what? I am cascading system 1, system 2, system 3, where system 1 belongs to this, 2 belong to this, 3 belong to this. So, this is the cascading method. Okay. So, here you can see my transfer function y s of u s can be written as this one, y s over x 1 s, x 1 s over x 2 s, x 2 s over u of s, right. So, y s over x 1 of s can be written as this one, you can say y s over x 1 s can be this one, and x 1 s over x 2 s can be this one, and x 2 s over u of s can be this one. So, here I am assuming these 3 part. Okay. So, if with respect to diagram, this is part number 1, and if we see b part plus b 1, you can say this is the second part and this is the third part. The same step I need to multiply numerator and denominator by highest power of s. So, here highest power of s is you can say 1. So, I will multiply numerator and denominator by s inverse separately. After doing that, I am obtaining this transfer function. After doing this step, I am getting this transfer function. Okay. So, first I need to model this as we have done earlier. Okay. So, this will be my system 2 and this will be my system 3. Okay, B 1 and A 1, sorry, B 1 and A 1 that I am keeping here. So, this would be my system 2, this would be my system 3, and this k would be my system 1 because it is single constant. So, I am modeling here k, then this system, then this system. This is the basically cascading, we are connecting them in series. Okay. So, this is the representation of SFG. Now, we have to look for the available of state variable. Whenever we complete this diagram, the first node would be regarding the output. The first variable would be here x 1, next state vector would be x 1 dot, then here we will get here x 2 dot. Okay, this is x 2 and x 2 dot, this sequence we need to follow basically. If you solve generalized basically, because if you see this loop, this is x 1 dot is here, x 1 is here and output y is coming here. If you solve this, though s 1, sorry, this is s inverse is here and b 1 is here, they will make a single expression. S inverse B 1, right. So, I can say in between these two nodes I am getting the single state vector, that is x 1 dot. Similarly, I can say here that this is my, if it is my x 1 dot, because here gain is 1. So, this node is also equivalent to x 1 dot, right. So, here S inverse is present multiplied by B 2, this will make the single node, x 2 acting as a here dummy node here. So, I can say my next node would be here x 2 dot, here x 2 and x 1 they are acting as dummy node. Basically, they are telling you the gain of the path is S inverse B, here it is x 2 dot, here it is x 1 dot. So, the sequence that we have to follow in CCF, same sequence we have to follow. It means the lowest state vector x 1 near output, highest x 2 dot state vector near the input. Okay. This convention we need to follow. Now, we need to write the expression of this state vector. Okay. So, x 1 dot can be written as, if we observe this state diagram. So, it is equal to the signal coming from here and one signal coming from feedback. Okay. So, what is the value of signal coming to this node that we have to see. Okay. So, x 1 dot is equal to one expression, you can say this node receiving signal from this part and this part. So, it is combination of two expression. So, this one is what? It is 1, right. You can say x 1 dot is basically equal to what? This one part. What is basically the variable here? X 2 dot. So, x 2 dot is coming to this node. So, I am writing the term x 2 dot. Second term is here, this node dummy node is here x 2. So, B 2 x 2 is coming here at x 1 dot. Okay. So, I am saying this is B 2 x 2. Now, the total expression in this node is x 2 dot plus B 2 x 2. Okay. Now, this node receiving one signal via this path, what is the gain? Minus of A 1 x 1. So, I can write here minus of A 1 x 1. So, the total expression of x 1 dot is given like this, x 1 dot equal to B 2 x 2 plus x 2 dot minus A 1 x 1, right. In the same way, we can see the expression for x 2 dot. Where is my x 2 dot? This is the x 2 dot. It is getting the signal from input and one signal from this path. The value of this path is k times of u. So, k times of u coming equal to x 2 dot. This is the feedback minus of A 2, here variable dummy variable is x 2. So, I will write minus of A 2 x 2. So, x 2 dot is equal to given by this expression. So, x 1 dot is equal to this expression, x 2 dot is equal to this expression. Now, with the help of these two expression, we have to obtain the state matrix. In the state matrix, we are knowing that in the LHS we are getting the derivative part only, but here we are getting derivative part in RHS. So, I have to replace this x 2 dot via this expression, and this will change my equation of x 1 dot. After doing this step, I am getting x 1 dot equal to like this, like this expression. If I solve it, this will become the expression. Okay. So, this will make my question number 1, this will make my question number 2, and then I will make my matrix, state space matrix. So, x 1 dot x 2 dot will come here. The first coefficient of x 1 is minus A 1, coefficient of x 2 B 2 minus A 2. So, I will write this term x 1 x 2, this is my first row. Second row will complete by the equation number 2. So, here x 1 term is absent, it is 0, x 2 term is minus of A 2, then plus k u is here, it means it is the input. So, one matrix for input u and k is a constant for it. So, this is my A matrix, this is my B matrix. Now, what about C matrix? It means we need to write expression for y, then I will get the C matrix. So, what would be the expression of y? It is combination of two signal coming from here, you can say this feed forward path and this path. Here x 1 dot is present. So, I can say here y s equal to x 1 dot, because gain of this path is 1, and second is coming from b 1, you can say dummy node x 1. So, I can write plus x 1 b 1. So, here this is my expression for y. So, again for state variable I have to keep my derivative part in the LHS. So, I will put here value of x 1 dot from this expression in the y, and after keeping this would be my expression. Okay. Now, I will separate out in terms of x 1 and x 2, and this will come. So, here x 1 coefficient is b 1 minus a 1, x 2 coefficient is b 2 minus a 2, and plus k u. So, this is making my y matrix, this is my C matrix, and this is my D matrix. So, now D matrix is coming in the picture. Okay. So, here you can see this D matrix is what basically it is telling us the forward path, right, or we are bypassing the input throughout the system. How we are bypassing the input k? You can see we are starting this k here, then we are jumping here, bypass it, again we are jumping here, bypass it, and it reaches to the output y of s. That is why this k u is coming in the feed forward path or in D matrix. This is also known as coupling matrix, where we are coupling our input directly to the output. Okay. So, this is the cascade method. Our next method is here parallel or diagonal method. Okay. So, this method is parallel form or diagonal form. Okay. So, by mistake I told that cascade will gives you parallel, sorry. Okay. So, here parallel form and diagonal form would be the third format to obtain the steady space model. Okay. So, in this case what we will get? We will get our steady space model with diagonal elements. Okay. How? We will see. So, here we need to consider this expression. Okay. So, this is my generalized transfer function. I need to represent it in terms of factored form, so that we will get here poles and 0. So, I am assuming that my numerator part is p of s and denominator part is this much. Okay. And I have to use here partial fraction method to separate these coefficients. Okay. So, with the help of partial fraction I will separate the poles, that is s plus a 1, s plus a 2, s plus a n, right. So, in this way I will obtain my transfer function in terms of this partial fraction. Okay. So, now where k is constant, this is my y of s, I will multiply u of s everywhere. So, this expression will become, you can say u s with the first k 1, u s with k 2, u s with k nth term. Okay. So, here we need to assume our x 1 as, you can say, state vector will be this one, x 2 state vector would be this one, in the same way nth state vector would be this one. Okay. So, y s can be written here in terms of state vector x 1 as the y is equal to k 1 x 1, k 2 x 2 till k n x n, right. Or here if I write this in terms of matrix y is equal to k 1, k 2, k n, and this would be my state vector x 1, x 2 till x n. So, this is my C matrix and this is my, you can say, state vectors, that is nth vector will present here, right. Now, what would be the value of x 1, x 2, x n, and how to represent it? So, here x 1 s is given as this, x 2 s given as this. So, we will separate out x 1 s, separately we are writing x 2 s, separately we are writing x n of s. Okay. If I solve this by cross multiplication, we will get this expression. If I take the Laplace inverse, I will get this expression. Okay. This is the case. In the same way, x 2 s cross multiply and then you will obtain this expression, obtain its Laplace inverse in time domain. Same step you have to follow here. Now, we need to draw the SFG for it. Okay. So, what will be the SFG? We will see here. So, for first case, this is d x 1 over dt a 1 x 1. So, I will assume as x 1 dot equal to u minus a 1 x 1. Okay. So, x 1 dot is my state derivative, u is the input and x 1 is my first state vector. So, what would be its diagram? You can say this is my x 1 and x 1 dot is here. You can say this is the x 1 dot. Okay. So, this x 1 dot basically come from this d by dt of x d by dt of x 1. So, this is s of x 1 plus a 1 of x 1. So, I have to obtain this s term is present, I have to obtain x 1 from s times of x 1, it means I need to add here a integrator. So, here I am adding integrator s inverse, this is s times of x 1 what is here, and here I will obtain the x of s. Now, plus a 1, so I will add here this thing because x 1 dot is equal to u minus a 1 x. So, it will receive the input u with coefficient of 1 and minus of a 1 coefficient coming from this feedback. In the same way, x 2 dot, this is my x 2 dot variable and it is equal to u minus a 2 x 2, it means it will receive u input with coefficient 1 and it will receive x 2 with coefficient of minus of a 2. In the same way, for another term I will get, this is the x n dot, this is x of n, it is u with coefficient 1, okay, minus a n will come in feedback. In this way, this will make a parallel SFGs, right. So, this is the end of this parallel method. Okay. So, here if we see the matrix, so we will get all the element in a diagonal way. So, first coefficient a 1, a 2 till a n, they will come in diagonal method or diagonal way, that you can say. So, this is my A matrix in case of parallel form or diagonal form. Okay. So, remaining step, that is a Jordan step, we will discuss in the next session. Thank you for today.